Hi guys, and welcome to the continuation of our 4-graph sojourn through our Methods 1 and 2 course. We've already dealt with rectangular hyperbola and the truncus, and today we are moving on to the square root graph. So do me a favour, please have a go at these questions from the Cambridge Essentials textbook. And those of you who are following outside of my lesson and in internet land, hi, welcome. Thanks very much for taking the time and coming to see me. This one's going to deal with the square root graph. You don't have to worry about doing questions. Just listen along and hopefully I make sense. So as I say, recap, we've already dealt with the rectangular hyperbola. So if you remember, the rectangular hyperbola looks like that. And if you do that in your exam, you'd have lost pretty much all of your work, or all of the marks. And the truncus looks like this. And again, that is two really bad diagrams of what these graphs are. But that's not the point. With each of these, this had the equation y equals 1 over x, and as such had two asymptotes, if you remember. And this one here had the graph of 1 over x squared. With how many asymptotes? Yep, 1 and 2 again. So knowing where these asymptotes are and the base graph's really important. Also to remember that you will then be able to transform these using DRT. Really important. You've got to make sure that for every single function, domains, ranges, important points, and asymptotes are all there. Right? I say, and I keep saying this, guys, really, the base graph is really what you should be drawing first, and then using that, building up your transformations to get you to your final graph. Don't think that you should just be able to draw this thing straight off. Sometimes you will, but many times you won't. All right, so let's start. Here we go. The excitement is building. This, ladies and gentlemen, is the graph, otherwise known as the square root graph. The equation is given by y is equal to the root of x. And as you can see here, it has this point here at 0, 0. So that's critically important. The base graph starts at 0, 0. And it has this point here, 1, 1. Funny how that seems to appear on so many different graphs. If you remember then, the next important point, and you wouldn't have to do this, would be 4, 2. Why? Because you are trying to get the square root of each of the x values to be the y values. You'll notice that actually the graph is not defined anywhere to the left-hand side of the 0. So there is nothing there. Why? Because you can't have the square root of a negative number. Right? So that's actually pretty good, but you'll also notice it's not defined, or there doesn't seem to be any part of the graph that falls below the x-axis. So nice quick sketch whenever you're drawing a root graph, and there you go, y, x. Are there asymptotes? Nope, there aren't any asymptotes. There's just sections of the graph that are undefined. So like in this situation, whole sections of the graph that are undefined. What are the domain and range of this particular function? Well, if I make this slightly smaller, then we've got it all in here on this sheet of paper. Or rather here. So what do I say? Helpful points 1, 1. Yes, domain and range. Now, the domain, and I'm going to rewrite it just so I can explain it, is equal to r plus. Now, r plus means all positive real numbers. But what you've got to realize is 0 is neither positive or negative, or it's both, or it just confuses me completely. But r plus does not include 0. So you have to say or 0. You have to put that as your domain if you're going to use r plus notation. The other way to do it is probably, as many of you would want to do, 0 to infinity. Okay? Either of those, totally acceptable. Same for the range. You'll notice that the range, which is possible y values, seems to start at 0 and go up and up and up and up to infinity and beyond. So again, the range could be expressed as r plus or 0. Or, again, 0 to infinity. Now, a small point about the notation here. If you were to do r plus n0, this actually means and. So what you're actually saying there is that our x values can take two simultaneous values. It can take any of the real numbers and it can take 0 at the same point. It can't, all right? You must make sure that your notation is with this u, union, or symbol, so that you actually can get the marks. Again, as I say for every single one of these graphs, the shape, it is critical that you know how to draw this. Knowing that, believe it or not, is pretty much the whole lesson. I kid you not. We can make these functions look all sorts of different ways. So if we assume this one here is my base function, which it is, I mean, there's no assumption needed, then we can put a +3. We can multiply the base function by 3. We can do this. We can multiply the base function and seemingly put a -5 under there. We can write it in a completely different way, or we can just make it look gross. And as I'm sure you're all aware, these are actually examples of dilations, reflections, and translations. So in this situation, the base graph has none of them. This +3, because it's inside the function or inside my square root, as I think of it, it's going to be translated 3 units the opposite direction. So that is a translation 3 units to the left. This one here, because that 3 is multiplying my whole function, this will be a dilation factor 3 away from the x-axis. Okay, so what was that? That's a dilation, factor 3 away from the x-axis. Here, we've got 2 combined. So first things first, we're going to have to do the dilation first. So the dilation is factor 2 away from the x-axis, followed by a translation of 5 units parallel to the positive x direction, as we put it. Now, this here is a BFT. It's a massive big fat trick. Why? Generally speaking, no, I keep saying generally speaking, why? We need to make sure that our x has a positive 1 coefficient, or a coefficient of +1. It doesn't here, so it's trying to trick us. I'm going to rearrange this to become -x plus 5, and then I'm going to take out that -1. Does my x value now have a positive coefficient of 1? Yes, it does. So it means that this -1 stands for one thing, and this -5 stands for another transformation. What? Well, we've already noticed that this one here is actually going to be a movement of 5 units. That way it's a translation, but what does that -1 sign mean inside? When there's a minus sign outside, it reflects in the x-axis. So actually our -1 is a reflection in the y-axis. Really, really important that you get this right. And we'll do a little more about this in a moment. Here, we've got everything. We've got absolutely everything. So if we look at our dilations, we have here factor 4 away from the x-axis. Wow, what else do we have? Oh, hold on a moment. We've got a 2x. We don't want a 2x. That's actually going to make things complicated for us because we always want a positive 1 value. So I'm actually going to rewrite this. It's not going to affect my dilation outside, but I'm going to write that as 2x plus 5 on 2 plus 3. All right, so dilation there. This one, and then there's going to be a dilation of factor 1/2 away from the y-axis. Why? Because it's inside that square root sign, so it's going to do the opposite of what I'm expecting it to do. So in that case, it's 1/2. Do I have any reflections? I should go, because we had that minus sign outside of my square root sign. So that's a reflection in the x-axis. And then we have 2 translations. We have a translation which is going to move me that way, 5 on 2 units, and then a translation that way of 3 units. That's the +3 on the end. So being able to break this down is actually going to make our lives much, much easier in trying to draw them. As you are aware, because I do it in pretty much every video in this series, please remember that the order of transformations is really important. If they don't give you an order, if the question doesn't give you a specific order, you must use Dr. T. Dilations first, then reflections, then translations. So when you look at a formula, always try and break it down into 3 important composite sections or composite parts. So let's deal with each of those in isolation. Reflections of the square root graph, we've already talked a little bit about it in some of those examples, but when you reflect in the x-axis, if you remember, the graph would become minus the root of x. That minus sign is outside of the square root sign. If that's the case, it is a reflection in the x-axis. My point here is still at 0, 0 for reflection. My important point becomes 1, -1, or my helpful point, and my domain and range now flip. All right, the domain actually stays the same. Sorry, I said it flips, I meant the range. But the domain still goes from 0 to infinity. But in this situation, the range goes from -infinity to 0. Yeah, because the range is now underneath the y-axis, so it goes from minus infinity to infinity. That's a reflection in the x-axis, and as I said a moment ago, when you have the minus sign inside the square root sign, that's a reflection in the y-axis. So reflection in the y-axis, once again, for the base graph, that point is anchored to 0, 0. My helpful points in this situation become minus 1, 1, because that reflection takes all of my x values and makes them negative. And my domain and range. Well, as you can see here, now I've said that my domain is r minus with 0. Right, now r minus in the same way as r plus means all negative real zeros or 0. That can be rewritten as minus infinity to 0. So there's my range. Sorry, no, there's my domain. And my range, because it's on the positive section, is equal to 0 to infinity. Now, a word of warning or a word of helpfulness again. Please, please, please start expressing domain as x is in, and then the range should be f of x is in. The examiners will be looking for this, and that's the type of notation. It's not wrong to write domain equals and range equals, but just where you can start using that notation, because when you get to SACs and stuff, it becomes really important. So those are the only two reflections. You'll notice they're both very different. What about dilations away from the x and y axis? These work in exactly the same way of things we've had before. So when you're dilating away from the x-axis, it's stretching away that way by changing my y values. Here, we notice the 3 is outside of my function or outside of that square root sign. That tells me it's the dilation away from the x-axis. It's changing my y values to make them 3 times bigger. So that's why it's changing the y values. Hence, once again, for the standard graph, that point is anchored at 0, 0, but my helpful point becomes 1, 3. The y values have been tripled. The sooner you actually start getting this and practicing it and actually using that language when you start looking at functions, you honestly, methods 1 and 2, methods 3 and 4 will be awesome. Domain, as we can see, is 0 to infinity. All right, so that would be x is in 0 to infinity, and my range, which would be function of x, is in what? Well, again, it's positive, and so once again, 0 to infinity. We would expect that because actually it's dilating away from the x-axis, so it's just stretching further up. A dilation away from the y-axis. Right, so what are we trying to do? Well, in this situation, we're stretching this way. Now, here is the value we are looking for. If it's inside the square root sign, it will be doing the opposite of what we're expecting it to do. So whereas it says 3x, it actually means that we are going to be dilating all of my values a factor of 1/3. That's interesting. So what was the standard graph? Well, the standard graph was 1, 1. Sorry, or my standard helpful point was 1, 1. So we're now saying that rather than changing the y values, we're changing the x values. So my helpful point in this situation would now become 1/3, 1. Is that true? Is it 1/3, 1 for my graph? Well, my graph is this one here. So this is the actual graph. Is it 1/3, 1? Where is 1? There. Does that seem to be about 1/3? I should go. Yeah. So we probably wouldn't put 1/3, 1 as my helpful point, which is generally why we would actually express 3, 3 as my helpful point. What is this other graph all about? Well, actually, as it turns out, this is my standard graph. So I put it on here to help you guys actually compare what it was like. So here is my normal 1, 1, which has moved this way, which is expected. It's moved 1/3 or scale factor of 1/3 closer to the y-axis, or it's multiplied all my x values by 1/3. So here is my original point, 9, 3. Why? Because x is 9, y is 3, square root of 9. And yet what you notice is that my x value has basically been 1/3. Right, so that graph was there, nothing more than to try and explain to you how that graph is looking. Translations parallel to both the x and y axis, nothing majorly difficult here, except when they give you these graphs in an exam. Always look at this point here. Because wherever that point is an automatic indicator of a translation. 9 times out of 10, you'll be able to look at that point there and you'll be able to find values of your translation. Now you're going to say, why would that be important to me? Well, it just so happens there's a lesson coming up later on about fitting this stuff to graphs. But as we can see, when it's inside the square root sign, it's a horizontal translation in the opposite direction of what you're expecting. So -3 moves it that way 3 places, which moves this point here now to x is 3, 0. And because my x values have all moved to the left, what was 1, 1 now becomes 4, 1. Domain? Well, the domain, remember, is possible x values. It's starting at 3 and seems to be going on to infinity and beyond. And my function, my range is the same as always. It's 0 to infinity. Why? Because we haven't moved it vertically. Why would my range change? It has no reason to change. Here, when we move the whole graph up, so this time we're translating positive direction. Once again, this point was 0, 0. It's now 0, 3. So I should be able to look at that and go, oh, hold on a moment. I now know that that's been translated 3 units vertically, which actually, interestingly, then helps me find, I didn't write my equation on this one, that y is equal to root x plus 3. So that would help me find that value outside of there. Everything else is the same. Because the graph's been moved up, my y values have changed. So what was at 1, 1 now moves up to 1, 4. My domain is in, that's actually 0 to infinity. I haven't moved it horizontally, so there's no reason for my base graph to have changed. And my function of x, otherwise known as my range, becomes 3 to infinity. So those are the basics. But obviously, in an exam, you're going to want to be combining transformations for that square root graph. Ooh, now here we go. Here is my original point that has moved. So it's gone from 0, 0. It is now -4, what would that be? 3. So -4, 3. We've got a helpful point of -3.5, 4. So I haven't actually put my original equation. I don't actually have my original equation. I normally put all my equations on here, but what on earth happened here? Well, and I know this is shortcut into a later lesson. We know the general form of this would be a root of x minus h plus k. For example, where h is a horizontal translation and k is a vertical translation. Because my graph has now moved to -4, 3, I would know that y would be equal to a, the square root of x, minus h, which would be +4, and then +3. So I'm almost there. That's like awesome. But how do I now find my value of a? Well, to be able to do that, I would need to know one other point. And lo and behold, I would now know that 4 is equal to a times the root of x, which is -3.5, plus 4, plus 3. Using this information, I now know that take away 3 from both sides, we get 1 is equal to a, multiplied by the square root of 1/2. Ooh, so what do we do now? What can we do now? Well, the square root of 1/2 is 1 over root 2. So 1 is equal to a times 1 over the square root of 2. So a would thereby be the square root of 2. So my function here should be y is equal to a, which is root 2, times the square root of x minus, x plus 4 plus 3. Well, that looks horrible. I mean, what's that all about? Well, it just so happens that when you do a root times a root, you can actually do everything times that. So it's 2x plus 4 plus 3. And I'm actually going to leave it like that. Now, this was rushing forward ahead to a graph, but this is how you would use information. But what we can see now is that actually my graph has been dilated from the y-axis by a factor of half. It has been moved 4 units to the left and 3 units up. Now, whenever we do these type of graphs, if you remember, not only do we have to sketch it, we have to show important intercept points. And as we can see here, for the graph above, we would be expected to use a CAS to help us find that information. All right. If not, if you didn't have a CAS, then what do we know at that point? Well, we would be knowing our equation would be the square root of 2, x plus 4 plus 3. At this point here, the x value is 0. So y would be equal to the square root of 8 plus 3. And you would use your calculator to help you find that. Or you would just leave it as 3 plus 2 root 2. All right, so just in case you are not aware, the root of 8 in surds simplest form would be 2 root 2. Now, there are tricks. Beware that the exam will always test your understanding. It will not just get you to draw base graphs. There's no way it will do that. We're looking for those tricks where that minus sign is after the number, so that we would rewrite that equation and we would have it as minus x minus 4. That would now tell me that that is reflected in the y-axis. So it would do that, and then it would move 4 units this way. So my final graph would look like that. All right. We need to be careful again with situations like here, because we want x to have a coefficient of 1, a positive 1. So that would be rewritten as 2. X minus 2, as I say here. All right, so that's a factor of a half from the y-axis and then 2 in the positive x direction. I can't say it, and I keep saying it, and I'll keep saying it, and I'll keep saying it. Whenever you are given equations like this, please, please, please make sure that you try and break down in your head what the dilations are, what the reflections are, and what the translations are. Well, that's it. The square root graph is done. Thank you very much. It's one of the most important graphs used over and over again. It's been great having you. I look forward to seeing you next lesson, which is on circles. Thanks so much for joining us for that video. It was really good having you. Now, if you'd like to know when the next video is coming, why not click on subscribe? Alternatively, head on over to MaffsGuru.com where you can watch all of the videos on its own dedicated website. While otherwise, watch the video that's just popped up. It'll be part of this series. All right, take care. See you again soon.